Okay, so I hope you're all prepped up after the first two questions, which were easy peasy. We now have the third question, which is going to be slightly difficult. So the question states that there's a particle of mass 2 kg which is undergoing SHM about the origin along the x-axis with a potential energy varying according to ux is equal to minus 2 plus 8x square. The maximum mechanical energy available in the system is 30 joules. What you've got to find out is the angular frequency, the amplitude, and the maximum kinetic energy. Now with these kind of questions, there is a certain first step involved with it, which Naveen is now going to discuss.
See, generally when you face these kind of problems, the first thing which should come to your mind is somehow this potential energy should be related to the equation of motion of the particle. So from the previous chapters, what you have learned was minus dou u by dou x is force. So when you differentiate this u, you get it as F is equal to minus 16x. So F is proportional to the displacement of the particle. From this we can say that the particle is in SHM. And then F is also minus kx. So from this you get k as 16, but k is m omega square.
So m omega square is 16.
So substituting mass as 2 and then you get omega as 2 root 2.
So we've now found the angular frequency.
Yeah. This is the answer for the A bit, and then when you go to the B bit, we need to find out the amplitude of the motion. When the particle is at maximum displacement, that is at the position of amplitudes, the whole mechanical energy is manifested in the form of potential energy. Because the velocity is 0, the kinetic energy at amplitude is 0. So potential energy at amplitude is equal to total energy.
Alright.
So U of A is equal to 30, which is given. From this you get minus 2 plus 8A square as 30, which implies A is equal to 2.
Okay, so we found the amplitude as well. And now we need to find the
kinetic energy.
Okay.
So total energy is equal to potential energy plus kinetic energy.
Okay.
The maximum kinetic energy is shown when the potential energy is 0. So when the potential energy is minimum. So this can be written as potential energy minimum plus kinetic energy maximum. But a minimum of potential energy is minus 2 plus kinetic energy maximum is equal to 30. So from this you get the maximum kinetic energy as 32 joules. So you could do some verifications or checks for this question. You can find out the maximum velocity from this kinetic energy which you got, which will be 4 root 2. And you can even get the velocity maximum which is omega A, which you have found out in the first 2 bits, that is also 4 root 2. So from here we can say that our answers are right. Like these kind of checks are useful in the exam.
Alright, very interesting, Naveen. So I think what we're taking away is the first thing we've got to write or try and derive is the equation of
motion.
Once we're done with that, I think the procedure is fairly straightforward.
Yeah.
We should also remember to be able to cross-verify our answers with things like these, because it sometimes does appear to us that how can the maximum kinetic energy be greater than the total energy of the system?
Exactly.
And this question is specifically being used to demonstrate to you that something like that is possible, because the potential energy can take on a negative value based on its distance from what we consider to be equilibrium position or any of these things. Naveen, what do you think the minus 2 in the equation implies? When u is equal to minus 2 plus 8x.
Yeah.
What does minus 2 imply as such? Because in this, when we try to conceptually understand the idea.
See, what it implies is at the equilibrium position we have considered the potential energy as minus 2. As you already know that potential energy is a relative term. So you can take potential energy 0 at any point. Suppose in this given question this is x equal to 0 and it is oscillating with an amplitude 2. So at 0 we have considered the potential energy as minus 2. That means we have taken the potential energy 0 at some other point.
Okay, so this basically shows how potential energy is always a standard that we choose to set.
Exactly.
Alright. So I hope you've learned enough from the question. Let's move on to the next one. Alright, now that you've tried out some easy problems, let's try solving a complicated one. Now what we have is, on a frictionless floor, there are two blocks A and B, each which has a mass m. A is fixed with two springs of spring constant k to the wall as shown in the figure, and block B has an initial velocity of v. Now all the collisions are completely elastic. What we have to do is find the time period of the resulting periodic motion. So Naveen, what is the first step you think we should go ahead with when we're trying to solve this problem?
Yeah. First, we need to analyze the motion so that we can calculate the time period of this particular system.
Okay.
So how does the motion look like? It's given as it has velocity v. So first this block B will be going towards A, and at some point at some instant of time it will be hitting A, and since the collision is completely elastic, A will be moving towards right to some point Z say, and then from Z it will again come back to this position where it will hit back B, and then from B it will again go back to this position and it will be hitting the wall. So it will again regain the velocity and again come to right. So this motion will be repeating. So this is a periodic motion which will be repeating.
So this is not an SHM, right?
Yeah, this is not an SHM from this basic analysis.
But can it be an SHM?
No, it can't be an SHM because force is not proportional to displacement at each and every instant of time.
Okay, so because we are going to continuously keep having collisions.
Yeah.
So, but will the motion be simple harmonic if we look at it for time periods in the middle, say, as opposed to 0 to t, 0 to t end, we look at it from t1 to t2?
I'll discuss that in the problem.
Okay.
During some periods it will be in SHM.
Okay, so let's see how we can break it down into the specific sections that Naveen has mentioned, where it moves from x to y and then block A moves from y to z, and then it comes back and then hits B again. So Naveen.
So from x to y, let the time taken for the motion be t1, which will be equal to distance by velocity, which is L by v. So at this instant of time, B will be hitting A, and since it is completely elastic, the velocity of B will be transferred to A, and then B will be coming to rest. So
now we know that at position y, when B hits A, B stops.
Yeah, and then A will be gaining that velocity.
The same velocity because it's completely elastic.
Yeah. So to calculate the time which it takes to go from y to z, you can do a simple analysis again. This is a spring block system, but there are two springs. So let's simplify that part first. Since the springs are in parallel, both the springs can be replaced with an effective spring constant of k1 plus k2, which is equal to k plus k is equal to 2k. So both these springs can be removed and it can be replaced with a spring which has spring constant 2k.
Okay, so we simplified a part of the problem.
So this part of the problem, the motion from y to z, you can observe that it will be in SHM, which is your normal spring block system, horizontal spring block system. So if you give a velocity v for this block, it will be executing SHM. So the time taken for this is, the time period of this kind of motion is 2 pi under root m by k.
Okay.
So time period is 2 pi under root m by k effective, which is 2 pi under root m by 2k. But this is to go from here to here and from this point to this extreme and then again come to the mean position. But that is not happening in this question. What is happening is it goes from y to z, comes from z to y, and again it will be hitting the block B at y. So for y to z, it is
half of this time period.
It is 1/4 of this time period.
Exactly, because it goes from the mean position
to
the
one
end
extreme.
position.
Yeah.
And we're only calculating it up to that, and that's just 1/4.
So T2 is T by 4.
Okay.
Similarly for Z to Y, it is another T by 4.
Okay. So the total time taken to come back to mean position is T by 2.
Yeah.
Okay.
And then from here, this block A will again have a velocity V because the energy is conserved.
Okay.
It should have the same kinetic energy at this point. So it will again have the same velocity. And it hits the block B at position Y. So the block B will take that velocity V and A will be coming to rest. So for the block B to go from Y to X, it will again take the same time T1.
But won't the springs be acting on block A at this point of time?
Since it is completely elastic, the spring effect will not be there. If it is inelastic, both masses will be moving together.
Okay.
We have already said in the question that it is completely elastic. So B won't be sticking or that kind of thing.
Okay, none of that will happen. And also because now A will be back at rest position, right?
Yeah.
So the springs will be completely relaxed.
Yeah, completely.
Therefore, no
relaxed.
force from the spring will be present
Yeah.
the moment A comes back to point Y to hit B.
Yeah. So T4 is again L by V. So your total time is T1 plus T2 plus T3 plus T4, which you get as 2L by V plus pi under root M by 2K.
2K. Alright, and there you have it, guys. We've solved a very, very complicated looking problem in a very simple manner. And what needs to be taken away from this is we only need to be able to visualize the solution and break it down into different parts. That one must not get worried when they see questions which involve multiple systems and one object hitting the other object and 2 springs or 3 springs. Because as you can see, you can make 4 springs here, you can put the springs in series or in parallels, and we will effectively resolve it back into 1K effective. And then as you can see, we can break it down into 4 small parts, from X to Y, Y to Z, Z to Y, and then back from Y to Z. And when we've done something that simple, we can calculate it for each of those little bits and be able to come down to the answer. So thank you, Naveen. Let's move on to the next question and let's try and solve that. Alright, in the last question, we learned how to break down a problem into small parts of the motion and then try and solve this. Let's see if that approach is possible here or if that's redundant, but let's try and solve this question as well. This looks fairly tricky because we have 2 blocks of mass M and M1 and M2, which are obviously different masses. They're connected by a massless spring of spring constant K and are placed on a smooth floor. Now these blocks are slightly pressed against each other so as to compress the spring, and then it is released. What we have to do is find the time period of the SHM. What do you suggest we should do about this?
Yeah. See, as we have done in the first 2 parts, when it is given as time period of SHM, we can always solve it in 2 methods. That is the force method and the energy method. So let's solve this by using force method. I think energy method could be an assignment for you guys. So let's start now. This box is popping up in between.
Okay.
So the solution. So let's assume that since they are slightly compressed, let's assume that M1 is compressed by X1 and M2 is compressed by X2.
Before this, Naveen, shouldn't we discuss what are the different methods that one can use to solve a problem like this?
Yeah, any problem of this kind can always be solved by using force method and energy method. We'll be solving this by using force method. So we'll be drawing the FBDs and then get the force equation. From there, we'll be getting the time period.
So Naveen, tell me this. Is there any value proposition in solving using the force method or the energy method? Like, कोई सवाल आसान हो जाते हैं अगर ऐसे किया जाए?
See, generally problems involving rolling can be are easily solved using energy method. So I'll be taking up that next. And problems involving linear motion will be easily solved using force method. And one more general tip is, if you have more number of forces, go to energy method, because writing more forces in the equation requires more amount of time. So if you have more forces, go to energy method, or if the problem involves rolling, go to energy method. Or if the problem involves something like fluid mechanics, better come to force method. So it again comes from experience. This is all from the experience.
Okay, so I think
if you solve more number of problems, you will be understanding for which problem which methods will be effective.
Okay, so in this case, Naveen thinks it's a better idea to try solving it using the force method. Let's try doing so.
Yeah. So assume that the M1 is compressed by X1 and M2 by X2. So the total compression in the spring, which is X, is X1 plus X2, and L, as you know, is the natural length of the spring. So let's write a force equation for block 1. This is a block 1, and the only force acting is the spring force, which is minus kx. This is for block 1. So F is equal to minus kx. F is MA1 is equal to minus kx, which implies M d square x1 by dt square is minus kx. And then we write the same equation for block 2. Block 2 has force minus kx on to right, so you get F is equal to minus kx, and this is M1 and this is M2 d square x2 by dt square is minus kx. So these are the two force equations for the two blocks which we got from the FBD.
Naveen, in the second one, when we are trying to draw the FBD for block 2,
yeah,
shouldn't F be equal to kx because it's in the direction opposite to the initial force on block 1? Are we keeping the force in the direction of the force into account, or does that become irrelevant?
Yeah, we take into account the direction of force. Since the spring is compressed, since the spring is in compressed position, when you see in this figure,
okay,
it will be applying force onto left on this block and a force onto right on this block, and
okay,
this is what I have drawn in this figure.
Yeah, so but what I'm talking about is in the representation, one is a force acting on the left side,
yeah,
from the left side,
yeah,
another from the right side.
Yeah, this
they're opposite directions.
Exactly.
Right?
Yeah, I got your doubt. Fine. So these minus signs are with respect to x1 and x2. For the block 1, x1 is positive onto right.
Okay.
And for block 2, x2 is positive onto left. That is what we have taken in the question.
So which would mean that x2 in... So can we use multiple axes at the same time? Wouldn't x2 then become negative simultaneously?
Yeah. So since minus kx is onto left and x1 is onto right.
Okay.
So f is minus kx.
Okay.
And similarly for block 2 also.
Okay, alright.
The displacement and force are in the opposite direction. Like the displacement of block 2 is onto left, but the force is onto right. And similarly for block 1, the displacement is to right, but the force is onto left. That is why this minus sign has popped up.
Okay, alright.
So from the first equation, that is x is equal to x1 plus x2, let's substitute these. X is equal to x1 plus x2. X is equal to. Differentiate this with respect to time twice. So what you get is d square x by dt square is d square x1 by dt square plus d square x2 by dt square. So you already have the values for d square x1 by dt square and d square x2 by dt square from these equations, from the force equations of block 1 and block 2. D square x1 by dt square is minus kx by m1. So what you get is minus kx by m1 plus d square x2 by dt square is minus kx by m2. Minus kx by m2. So what you have got is minus kx into 1 by m1 plus 1 by m2. So from here you get your omega as under root k by mu, where mu is called as reduced mass, which is equal to m1 m2 by m1 plus m2. So what does this physically mean? This physically means that a block of mass mu is attached to a spring of spring constant k, and this whole system is in SHM. This system is equivalent to the given system in the question.
Oh, so this is fairly simple, wasn't it? What we've understood from this question are a multitude of things. The first is that when you hear the words time period of an SHM, you can easily go ahead and assume it to be one time zone and not have multiple time zones to worry about. The second thing we've learned is what are situations in which one applies the force method and what are situations in which one prefers to apply the energy method as such. And the last thing that we've learned is the concept of reduced mass, something that's going to be very useful as you move on to more complex questions, because that allows you to make a complicated system into one combined system, thereby easing up calculations as well as, well, making it easier to understand. And with this, I think we've solved the fifth question and we don't have any other concepts to cover with this. So let's move on to the next question.